my pleasure to introduce you to our project, MaLePoM, which stands for Machine Learning for Pollution Monitoring. As you can see, our project is trying to deploy machine learning techniques to predict emissions, in particular NO2 emissions and CO emissions. A brief introduction about our team. Next slide, please. So I am Luca Rampini, a PhD candidate from the Architecture, Built Environment and Construction Engineering department at Politecnico di Milano. And my teammates are Nicola Brunello, which is a master student in computer science and engineering, Paolo Fornoni, which is a master student in mathematical engineering, and Vidor Mittal, who holds a bachelor in physics. So as you can see, we are multidisciplinary teams with different backgrounds. So let's dig into our challenge. So basically, worldwide, the presence of nitrogen dioxide emissions is very important and has a lot of influence on human health and climate. These emissions are very correlated with anthropogenic activities, and nowadays, currently, there is only inventories that usually take in account these NOx emissions. These inventories have in particular two principal caveats, which are the first one, they are fixed or vary at a very long time scale. And the second one, they cannot capture slight variation such as diurnal variability or season-specific activities, for instance, traffic or burning crop. Next slide, please. Okay, so we divide our project in 6 main phases. So the first one is the data selection. So since a dataset for our purpose didn't exist, we explore many features and datasets available, in particular from Wikio, and we select the most promising, thanks also by the suggestions gave by the mentors. After the selection of the dataset, we explore better with the exploratory data analysis the features that we select and see how they are compatible with our target data, which are NO2 emissions. After that, we make some data engineering and we start to define our machine learning model. The last 2 steps comprises the publication of the results and also prepare the documentation that is available on the GitHub page of the project. Next slide. Okay, now we'll see in more detail the methodology that we used to perform the project. So the first part is more related to data science. So I will stress that there is no existing datasets to predict NO emissions. So the first step, which it takes one big part of this project, is to build and select different features and build a unique datasets. Then we did the exploratory data analysis, as we said before, and with data cleaning, correlation, and feature engineering, we select the final and the final dataset that we used for training the models. For the machine learning part, we start with a baseline model to use as a comparison with our more advanced and complex model, which uses recurrent neural network. So it is a long short-term memory model to predict the emissions. Next slide, please. So the aim was to find the suitable proxy for emission globally, to predict emission globally, but we have to deal with some limits and bottlenecks, in particular computational power, because we have a dataset with millions of records, so it wasn't possible to deal with a global dataset, but we try to focus on a specific time and geographical location. And in particular, we focus on an area in Central Europe with a resolution of 0.25 per 0.25 degree. And we concentrate on the 3 particular months where we had the target data, so the emissions, which are May 2019, July 2019, and May 2020. Moreover, the data availability was another limit or issues that we have to face, because not all the features that we select were available on Wikio, for instance, the traffic. So we had to deal also with this limitation. Now let's start to explore in more details the different phases of our project. And so I leave the stage to my teammate, Peter.
Thank you, Luca. So the first step is the creation of the data set, as Luca was mentioning. So the data we use in our project comes from various sources, primarily from Wikio, which is a source of lots of geospatial and climate-related data. And also some data sets are sourced from elsewhere, for example, here, which is a company that provides real-time traffic data. So we select data sets based on various conditions. So one is obviously the geographical availability and coverage of the data set, as well as the granularity and temporal resolution, as well as the scalability. So it has to be available for the entire globe for a model to be applicable on a large scale. So in the end, we select 4 final data sets to use in our model, which are the concentration of certain trace gases in the atmosphere, which is obtained from the CAM's global reanalysis and accessed through Wikio. Then we have weather-related parameters like wind, temperature, precipitation, etc., which is again obtained from Wikio, accessed through Wikio. Then we have land use and land cover data, which gives us information about different land use classes, which is obtained from the Corin land cover data set, and again accessed through Wikio. And the final data set is traffic, real-time traffic conditions, so traffic density, which is obtained from the Here Traffic API, which allows you to query traffic data in real time. So these are the 4 data sets that we use. So another important consideration while or before building the model is the choice of dependent variable. So initially, the plan was to use NOx as the dependent variable in our model, since NOx is an important anthropogenic pollutant. But after starting, we observed that NOx concentrations in the summer months tend to be very unstable and unstable because of high photochemical activity that NOx experiences. So this made modeling NOx particularly difficult because concentrations are very depend a lot on photochemical activity. So then, after discussing with our advisors, we were suggested that we can use carbon monoxide instead of NOx to build the model initially, because carbon monoxide does not have such high photochemical activity, so it's more stable, especially in summer months. So then we built our model on CO, and then later we compare results for CO and NOx. Next slide, please. Yeah, so the next step in the project was to conduct some basic exploratory data analysis and try to figure out what features might be relevant in our machine learning model to predict emissions. Next slide, please. So the first data set which we explored is the emissions data, which is the dependent variable in our model. So we find that the emissions data for our particular area which we considered, it seems to have a couple of outliers or points which may be reflective of some erroneous values. So from this plot on the right here, we can see that these 2 points, the orange and green lines, represent 2 points for which the values of emissions are consistently much higher than the emissions or the mean emissions at the other locations. So it's almost 1 to 2 orders of magnitude higher throughout the entire time period. So these are probably outliers that we have to deal with while or before building our model. So that is done by either dropping them or including that explicitly in our model. So next slide, please. So the land use or land cover data that we obtained from Corin, so that is actually an important spatial predictor for emissions data. So if you see the figure on the right, the top figure gives us the mean CO emissions for the month of May 2019, and the bottom figure gives us the percentage of built-up area, which is not temporally changing, but it's for the same location. So I see that there's a in general good agreement between the emissions and the percentage of built-up area, which is as you would expect, as urban areas tend to emit much more CO and NOx than rural areas. So it's important to note that the land use and land cover data, since it's temporally fixed, it only provides information about the spatial distribution or spatial variability of emissions rather than the temporal variation. Next slide, please. So an interesting data set to look at was also the traffic data. So we know that emissions typically follow a strong diurnal cycle, which has two peaks typically in the morning and evening. So in this plot over here, we see the orange line, which corresponds to the emissions profile, diurnal profile. And then looking at the traffic data, we find that the traffic very closely matches this diurnal cycle of the emissions. So the two blue lines here are the traffic diurnal patterns of the traffic data for two different points. The higher line is for Milan, and the lower line is for a point outside of Milan. So the peaks of the traffic match pretty closely to the peaks of the CO emissions. So we find that traffic is a potentially good proxy data set, which can effectively capture short timescale temporal variations in emissions. Next slide, please. So now to talk about the other data sets and the models that we used, I'll hand over to Paolo. Paolo.
Thank you, Vitor. The third dataset we will talk about is the concentration dataset. Here we have the data of some concentration of some gas in the atmosphere. And this dataset is very important in our model because we have the concentration of CO and NO2, which are the two gases that we're trying to predict. Managing this dataset, we can see that in some area, the concentration and emission are really good correlated, and so this dataset is also more important for our prediction. In the next slide, we will talk about the last dataset, the weather dataset. Here we have some features like the cloud, the humidity, the temperature, and to make a better correlation between this feature and the emission, we take the total wind, the temperature, and the humidity, and we shift this data some hour behind. In this way, we get a better correlation, and this will improve our model. Now we have all the data set we need. We can merge all this data set, create the big data set that we will use in our model. Next slide, please. The last part of this presentation, we will talk about the machine learning model. But before talking about the model we will use, we need to talk about the baseline model and also about the feature import analysis that we did. For the baseline model, we decided to use a linear regression. We used this model because we didn't need to pre-process the data, and we use a tenfold cross-validation. In this way, we can get some more meaningful value for the two statistical measures that we will use, which are the R square and the mean square error. For both the baseline model that we did, we got significant value for the two measures, but we can see that for the CO baseline model, we get better value, and this is one of the reasons that why we decide to put our effort in the predicting the CO than the NO2. In the next slide, we will see the feature importance analysis. From the graph, we can see the importance of the features using the Gini index, and we get that the most important features for our model are the length features, the traffic, and the specific humidity. Now we can start to talk about our final model. Next slide, please. Here we can see a framework for a generic machine learning model. We have some data, we put the data in the model. The model creates some predicted value, and we use this predicted value and the true value in the loss function to get better regressor, a better model, and a better prediction. This is a general pipeline for a machine learning model, and now I leave the floor to my colleague Nicolas, who can explain how we implement this framework in our project.
Thank you very much, Paolo. So let's take a closer look at our particular machine learning model. Starting from the input data, we can notice that they are both spatial and temporal distributed. In other words, the dataset lays on a three-dimensional space, which raises the complexity of the problem. Moreover, there is a large discrepancy among the range of features, especially the target emission values. But this is something that standard preprocessing techniques can easily solve. In second place, we explored many different models, and we came to the conclusion that neural networks are the most effective techniques, and in particular, recurrent neural networks, as my colleague said before. But the problem with this model is that they are really, really complex and takes a long time to train. Last point is about evaluation of prediction versus ground truth. So apart from choosing the loss function, we face the issue on how to evaluate our results. As we explain later, we decided not to rely only on the value of the loss function, which the lower it is, the better it is, but also graphically visualize our results in order to have an idea of our performance. So next slide, please. So this is an example of how data were presented to us. As you can see, the dataset is indexed by both latitude and longitude, and for pair of them, it contains all the time sequences. So we adopted two training methodologies. The first one is the basic training, so selected random subsequences from data and feed the model with them. But we noticed that in this way, there's some probability that subsequences take into consideration far away locations together. So in order to solve this, we created a custom training, we call it like that, which basically forced the training to select subsequences from the very same location. So next slide, please. As you can see from the slide, we tried 5 different final models. So the first is the empirical mean, acting as a baseline, of course. And then we have the standard neural network trained with the basic training technique. Then another standard neural network with the custom training. Then more complex, the recurrent neural network, long short-term memory with the custom training. And then finally with the recurrent neural network with the principal component analysis applied on the dataset. The best performing model is the fourth one, as you can see, which raised the lowest mean square error on the test set, computed on the test set. With this procedure, we saw that the best, but we want also to know somehow how much is our error in making predictions. So in order to do this, we plot data. So the plot on the right side you see is the plot taken from the best performing model of a subset of the test set. And in orange, there is the prediction. In blue, the ground truth, and in red line is the empirical mean. And as you can see, data prediction are quite imprecise. The error is quite high, it's not sufficient, but our model is quite able to capture the variability of the emissions. So the diurnal pattern and also the week pattern. So from this result, we can draw some conclusion. Next slide, please. First of all, we are quite satisfied with the dataset created. Since there is not similar project online, we had to create it from scratch, and it shows good potential to tackle the problem. Also, the models show a good pattern matching with the mission, but of course, right now it lacks of precision and single point prediction, which are the bad results still working on it. So for this reason, we strongly believe that our project is a starting point, since it shows promising result, which could be improved with the next steps. Showing the next slide, please. In particular, the bigger challenge here is to gather more emissions data, which are really rare and difficult to get. But having more data could lead to better precision and also pattern matching with seasons and years. Also, more hyperparameters tuning and more complex models should be followed. But the former require a lot of time and the latter requires large datasets. And possibly also explore and find out more reliable proxy data could be a way to improve performance. So next slide. So thank you all for the attention. We'd also like to extend a special thanks to our mentors who constantly supported us and guided us in this project, and also in all the people involved in the challenge, which gives us the wonderful opportunity to learn and get in touch with such advanced and promising reality. Thank you.
Thank you, MaLePoM, for this full and very interesting talk. And a pleasure for you to take part in ESO, for your motivation and enthusiasm.